Welcome everybody. This is Marvin from Elise. I'd like to welcome you to this expert session, Generative Engineering of AM Automotive Suspension Components. Let's wait a couple of seconds until everybody is in, and then we will start right away. Thank you. Okay, I think now we can start. Couple of persons are still coming in, but I think this is totally okay. So yeah, welcome again to this expert session, Generative Engineering of AM Automotive Suspension Components. Today it's all about how the method of generative engineering can be implemented in generative engineering companies, or engineering companies in general, and used also to increase the efficiency of early stage development. For all of your questions, please use the Q&A button in the Zoom menu. So yeah, in German it's F&A, Frage und Antwort. In English, Q&A, questions and answers, so that after the main presentation, we can discuss them together. If we can't discuss all of the questions, we will come back to them later on, but it's better to use the Q&A and not the chat, because we cannot get back to the chat questions as it's anonymous also. All right. So yeah, let's have a look. Let's have a look on conventional product development processes at the start, and I will give a quick introduction what our opinion is about generative engineering, and later on we will go more into detail. So let's have a look on the conventional product development process. It looks yeah, something like this. So at the end, we will have our final product, and we will always focus on the product itself. That's always in front of our eyes. So we would like to develop a part. In the beginning, we have our technical specifications defining all our material data, for example, in load cases. And then we have a serial process with a lot of iterations. So we develop our concept, we go to product design, we have some simulations ongoing. Then we take a look on the manufacturing pre-processing, and we do some cost evaluation. But for example, at this early stage of the concept development, we have no clue about the cost evaluation. So we need to go through all this process, and then we need to go back and forth and do some manual iterations. Of course, we have limitations in time, so it's only possible to do a few manual iterations. And also, these things are totally isolated most of the time. So the intersection, the interfaces at this point are the crucial areas. Here we have. I would like to welcome our external partner, Tilman Steininger from RLE. And he will later on tell us about the development process of RLE and how they implemented generative engineering, how they tried to overcome these iterative steps, and how to improve these processes. Okay, this is how we think of a generative engineering process should look like. So at Elise, we have also a technical specification. This is the same thing. So you have the same tech spec sheet, but then in the middle, you don't see a serial process. It's more a central process where the product design is in the middle. We have a lot of designing and evaluation cells, and they are interconnecting with our core cell here. So it's yeah, it's faster because we have direct feedback of all our evaluation cells in the same moment, and we can run more optimization iterations in an automated way. And this enables us to yeah, to improve this process, to overcome those boundary conditions, those boundaries between the different silos of CAD and FEM department, for example. And this is what we call the technical DNA. At this point, I would like to welcome also my colleague David Leidenfrost, who will later demonstrate an exemplary use case of product development live in EDs. All right, so Tilman, would you like to introduce yourself, and would you like to tell us more about RLE and how you make use of generative engineering?
Sure, can do that. So as you said before, I'm Tilman Steininger. Let me just share my screen. Give me a second. Should be that one. Okay. So just before introducing myself, I just want to say a few sentences about the RLE International Group. Currently, we are 2,100 employees with a yearly turnover of around about 150 million euro. That makes us to one of the global top 20s engineering service providers. And we are, and I think that's one of the important points while talking about RLE, we are still at that size of the company, we are still owner driven, and that's round about 35 years now. To say something about the RLE vision or the RLE concept, we are want to provide a full vehicle integration or full vehicle development with always the idea of zero emission. And therefore, we are working on all the development fields which are necessary for full vehicle development or full vehicle integration, for example, interior exterior development or body in white or closures development, electric systems. So for today's webinar, we picked out our chassis development cycle, which is based in the company underneath the technical units, kinematics and concepts, and the chassis development. The ELISE application or the ELISE workflow itself is based underneath digitalization and CAE. And to summarize everything inside of RLE, we are acting in the major fields, mobility concepts or total vehicle development. To say a few sentences about myself, I started at RLE around about 7 years ago now, at that time in the lightweight department. There, we were running several projects on, mostly with the major content on structural optimization, and my responsibility was mostly topology optimization, stiffness strength analysis, and a little bit of CAD design regards kinematics design and also castable design and so on. And after a few years, I switched to the RLE Kinematics and Concepts department, because on the one hand, I have always that background on kinematics, and I see my personal strengths on concept development. And I also think that concept development is one of the most interesting areas, and maybe also one of the important fields in the development process, because in my opinion, I think a proper concept phase causes less issues in the later on serial development process, and also the performance of every component becomes much closer to the optimum, or much closer to the lightest design, or let's say closer to the best balance between lightweight design and cost maybe. So for the last 2 years, I worked on several chassis programs where we basically started from scratch and ended in a physical prototype. And my responsibility there was technical lead and stuff like topology optimization again, and stiffness strength analysis, also the kinematics development. So I think from my side, that's basically all. Maybe Marvin, you have some questions on that?
Yeah, thank you. Thank you for the introduction to RLE and to yourself. You mentioned topology optimization and the kinematics, and a lot of other topics you're working with and tools you're using. So what inspired you the most about generative engineering, and how how did you come over it? How did you got interested in generative engineering for specifically your work in kinematics?
Sure. Yeah, basically the most inspiring thing on generative engineering is basically, or in my opinion, basically the huge amount of, or the huge potential of time saving. Because in my opinion, that ends in two scenarios. Maybe you can, and the one at first, you have the possibility to shorten your concept phase, which saves money and so on. Or the second way could be to keep the length of the concept phase and try more options, especially in kinematics. Is always helpful to try more options. And also you have the opportunity, if you have more freedom in the concept phase, to try more options, to come up with something unique or thinking outside the box. So I think that's the most interesting point on generative engineering, that huge potential of time saving.
Cool. Okay. Nice. And regarding RLE, what were the business objectives you had in mind you need to focus on?
Yeah, maybe this is something I can answer with our chassis development cycle, or our, let's say, conventional chassis development workflow. So there we had several issues. It's maybe not only our chassis development workflow. I think that's basically the common chassis development workflow. But at RLE or on every company also, I think the first step is always to run a kinematic development, where you have to take care on all of the chassis specific things like camber, cast, or toe curves, or roll axis, or let's say kingpin offset, and so on. And then you have to jump to that. Have to provide that cutting loads and all the kinematic points and so on. And then if you want to run a topology optimization, you have to create a design space, then run the topology optimization. Then you have to redesign the topology optimization, then run the part validation, and then maybe the system validation. And as I marked with that green arrows, and I think that's the question you had, inside RLE, we always had the issue that there is a huge amount of iterative processes inside that development cycle. Means, for example, that internal, or let's say internal iterative process from CAD design to validation. If you recognize issues in the part validation, for example, you have to jump back to the CAD design, or maybe you recognize huge issues in the part validation, you have to jump back to the kinematic development. Same for the system validation. If you recognize issues, then you have to step all these stepstones again, and that makes it really complicated, I think. And it depends on how experienced you are also. It could take a lot of time, or on how complex the system is. It could also cause a lot of time in there.
It looks like it's a lot of steps, and you have a lot of interfaces in between and coming from one to the other.
Exactly.
Thank you for showing our attendees the process you use currently in Elise at RLE. Elise is something that will come later. Okay. But of course, let's get even more technical. So we know your processes. Can you give us more insight into your technical challenge?
Yeah, basically the technical challenge is to achieve the targets without using that much iterations. That's the technical issue, we can say. No? So if you just have to run one loop, kinematic development, cutting loads, and so on, and end up in a system which works, there's no issue. But normally we have several options we have to try, and then after a proper kinematic development, you have parts which are green in the end, and then the system later on, much later in the development phase, you recognize there's an issue, and then you haven't got the maybe more often you haven't got the possibility to jump back to the kinematic development. So then you have to live with the kinematic you have, and the parts becoming heavier, or yeah, you're creating issues which you could achieve in the end. Yeah. So maybe to show, or yeah, maybe I can show this the cycle with Elise, or is that something you want to see later? Yeah. Okay.
No,
Then
yeah. That's pretty nice. Yeah.
So the workflow with Elise is basically so the stepstones are the same, or the development fields are basically the same. You will still have a kinematic development or part design and so on, but everything is highly automized, and that's the major achievement, I think, in the end. So if I go through that cycle, just to explain that, you have to start with the kinematic development, again with respect on all the chassis specific requirements. Then you have to provide an Excel file, for example, with all the content from the kinematic development, like kinematic points, forces, and what is maybe something which is a little bit specific on that kind of workflow. You also have to provide degrees of freedom on every component for later on system validation or part validation. After that Excel sheet, or after that process, you have to create a CATIA design space. In our case, it is CATIA. It could also be NX or something else. You have to create this design space. We manage that with an CATIA start part, which is easy to change or easy to update, because it could be that you have a controller maybe with at least six kinematic points, for example, one for the spring, one for the damper system, then you have one for the anti-roll bar, two maybe on 2 joints at body side, one on the wheel side. But it also could be that you have just a 2-point link, which could be a toe link or something else. No? After that, you provide all that input to Elise. So the design spaces, non-design spaces, and all the content out of the Excel file, forces, points, and degrees of freedom, and everything compiles automatically in Elise. So out of CATIA, this is basically, after we have created this design space, it is just a one-click solution, you could say. You press a button, everything goes out of CATIA inside Elise. And this, it's something like a CATIA gateway, you can say. In the output from Elise then is maybe something like a solid part, which appears automatically in your CATIA design space part. And that part you can then directly use in CATIA to redesign or to check the kinematics, to check collisions and so on. But that solid output is not just the only output on that Elise calculation. You also got the solver decks, or not just the solver decks, you also got the information about stiffness and strength or deflection values and so on. And you also get the solver decks of each component, which you then can use in your elastokinematic for doing, for example, a KNC analysis or just the elastokinematic. And this is something which we wasn't able before, because then these informations you can then directly use in the kinematic development in the beginning of the process. So all the flexible behavior of a full system is already an input for the kinematic development, which makes it much faster and less iterative. And this is something which achieves our process a lot and makes it a lot faster.
Wow, this is great to see. I think for a lot of our attendees, how an integrated process looks like for an engineering company, for an engineering service provider, for automotive industries. I think this is really useful. So you as attendees, you can, I hope now you have a better understanding how you could integrate Elise right now in this current state into your process. So there are a lot of tools we see here: Altera, CATIA, Excel. So the special tools, kinematic tools, of course, we see here they're not implemented right now in Elise, or we can't connect to them. But what you can do is that yeah, you can connect your most beloved tools with Elise and integrate it this way that yeah, we will come to this process. At this point, Tilman, what were the unique software features in Elise? Because here we see Altair, CATIA, some yeah, like, jumping back and forth. And what were the unique software features you liked most in the Elise process, which are unique?
There were, I think, several features inside of Elise, for example, something like the convert to quad mesh. So you have that meshed base or the ISO mesh, which is coming out of the topology optimization, and you can redesign that inside of Elise and get back a cleaned up model. But also the functionality itself is very interesting for us, that you automatically get back that solver decks, for example, or also the easy input to Elise. That's something which is very helpful. Or also we have always tried something to try overnight several material concepts, and that is also very easy in Elise to have a material table, and then you can automatically choose several materials, and it runs overnight with several aluminum versions, for example, and you get back at the end of the day or at the end of the night, you can say, several parts with several KPIs and so on. So that's pretty interesting.
Yeah. Okay. Oh, great. Yeah. So now, of course, we would like to learn more about these features and how they are working together. The suspension arm Tilman mentioned here is highly confidential, but we can have a look on a similar part. At the upright position, here you see that design space, that brown design space, and that is meant for a steering knuckle. And we have an exemplary use case very similar to this one. And at this point, I would like to introduce David. And David will give us insight into Elise and will go through a technical DNA and show us all the advantages of that. Hey, David.
Yeah, hi Marvin, thanks. Thanks a lot. Yeah, I'm David, responsible for the application engineering team at Elise. And I would also like to thank you to Tilman from RLE International Group, that they are really for joining the webinar, and also showing their current development process and how they tackle all these challenges with Elise. And because I'm quite sure there are a lot of engineers out there and companies who face similar challenges. And so, yeah, I think this is really awesome to see it.
And so thank you also for the invitation.
Yeah, and you don't keep that for yourself. So I think there are many people, they can see what's actually possible once digitalization, gets more and more common throughout all the companies. So I will now share my screen, and we can directly jump into the use case we have done with RLE together. So now you must be able to see my screen.
Yeah.
Yeah, is that correct?
Yes.
Perfect. So this is the Elise software, and on the left side we have here our canvas where we can generate a digital product development process, and on the right side we have here the viewer. And we are looking now at the steering knuckle workflow, but in general it always looks the same, no matter if it's the suspension control arm or even a tailgate. The process looks always the same. We have 3 steps, and the first step is always getting data from an external program inside, what we have seen in the slides before from Tilman, which was the CATIA interface. So here's all the data in the blue area, the data coming inside. And as you can see by all the blue cables, this data is then processed by many components and features like topology optimization, reconstruction algorithms, final element simulations, and so on. This all happens in a generative engineering section here in the middle. where based on the input data, a part is automatically generated. And then this part is evaluated in the green area regarding its mechanical properties, also manufacturing costs and CO2 footprint. And then in the last but not least, all these KPIs are summarized, can be exported for an Excel sheet to the PLM system, and same as the automatically generated part. And this actually sits in between these two CATIA gateways shown before by Tillman. Okay, let's jump into the first section, I would say, and let's have a closer look. So yeah, we are getting, for the steering knuckle, of course, we are loading inside some design space and some non-design spaces. And this happens through the import component. Yeah, and we can import here different formats like step, STL, cut part, cut product, parasolid, yeah, and so on. And next to this, we also need to import, of course, material data and the loads, which come from the kinematic program. And yeah, usually this information is saved into an Excel spreadsheet. We can open that here. So we have here our material data, scalm alloy and steel, all with the mechanical properties. And we also have here all the loads coming from the kinematic program with the applied load vectors and the different master points, the constraints, and also the target stiffnesses this part has to achieve. And all this information is basically through the Excel read function imported into RLEs. And here we can find again the linear elastic material properties of the scalm alloy, and here, for instance, our degrees of freedom, target stiffnesses, force vectors, and so on. And that's basically it. This is the step where we bring all the data inside of RLEs from an external programs. And now we can jump to the next section, the generative engineering section, where we are generating now, we are basically processing this information. So the first step is to create a mesh out of it. So, and this happens here in this cluster. And yeah, we can also jump inside, so it's a little bit less magic. So we can open one of these clusters. And there you will see here inside our solid mesh component, which basically is the first interface with HyperMesh, with Altair HyperMesh. So we are sending this imported design, non-design space information to Altair. And HyperMesh opens in the batch modus and is meshing the part regarding our parameters we have defined. So all the parameters you can define in Altair, we can remote control basically from RLEs. And once that's finished, yeah, we have our mesh. And the mesh is automatically back imported to RLEs. So this happens inside this cluster. So once we have our mesh, we can, yeah, in the next phase, we can define our RBE definitions, rigid body elements. And yeah, we have here imported our non-design spaces and our master points. And on all these master points, we applied then the boundary conditions here in blue. And these master points need to be connected to the corresponding non-design spaces. And for that, we can extract here automatically the cylindrical surfaces of these non-design spaces. And that's already it, because we only define a rule. We only define the rule, basically, that these blue master points, yeah, that there should be a spider between the blue master points and the, yeah, now blue reference surfaces. So basically, the rule says that all the mesh vertices which lie in the vicinity of these reference surfaces should be taken as target nodes for the RBE spiders. But we don't see them at the moment because we are only defining a rule. And this is also the great thing, because we are defining here parametric mesh independent setup. So if later on the mesh changes or the part changes, the rules is still applicable. And yeah, so we don't have to regenerate the RLE spiders. We are just creating the rules. Same applies to the boundary conditions. So on all these master points, we have to define now our boundary conditions, like the degrees of freedoms and the force vectors. So you can see here on some of them, some of them are constrained, and at the very tip of the steering knuckle, we have our unit forces applied. Yeah, and then in the simulation section with the FE model, basically everything comes together. So we have as an input our mesh, and we have the RBE, the rules for the RBE spiders and the load steps. So now these rules are applied to this mesh, and now is the first time we actually can see our RBE spiders. Yeah. So as I said, this is kind of a mesh independent definition of a FE setup, of a FE model. So if for any reason we want to change the element size or the part, these rules for the RBEs and the load steps are still valid. And this is a huge potential. Well, of course, we can then run a FE simulation with OptiStruct, and we can back import the results. So we can see here our reference simulation results, here the element stresses. And of course, the next step, usually we make our topology optimization. So yeah, the goal is to reduce mass and to still to create the lightest part possible, which still fulfills the target displacements. So yeah, objective is to minimize mass, and the constraints are to fulfill the target displacements, which we have imported before for the Excel interface. And also here we have the interface to Altair. So in the data is sent to OptiStruct, and OptiStruct is performing a topology optimization, and as a result, we are getting our ISOMesh. And now usually in the conventional product development process, we would now go back to our CAD system and rebuild this, basically create a solid part based on this ISOMesh. But also this step we have completely automated, and this is the quad measure Tilman has mentioned before, which is very, very powerful. So the ISOMesh exists out of many, many little triangles, and is most of the time not a very nice mesh, has many self-intersections and so on. And with the quad measure, we can generate out of this ISOMesh a really nice quad mesh. And once we have done this, we can use the sub-D algorithm to create a solid part out of this quad mesh. And we also have to, because in the sub-D, you lose all the sharp edges. So we have to make a Boolean again with the not sharp edged non-design spaces. So we bool them back to the smooth part, and that's already it. And we have our final part. Yeah, and in the last step, we can evaluate the automatically generated steering knuckle. And as I mentioned before, since we are defining everything mesh independent, our rules are still valid. So we just need to copy paste the container which contains the rule of the RBEs and the load steps. So you can see here these cables that run all the way back to our first section. And yeah, we only need to mesh the new part, and we can apply the same rules. And although we have now a different FE mesh, you can see that we can still, you see the RBE spiders are automatically generated. And of course, we can run our FE simulation, and we can see here the final result and the performance of our automatically generated upright. Of course, we can also evaluate the mechanical performance. So basically we are extracting the displacement responses of this part and the target displacement and compare it with the target displacements if they are all fulfilled. And it is the case. So all the displacement responses are smaller than the target displacement. So they are all true. We can also get out the weight of the part, calculate here the rate reduction compared to a reference part. And since our software has an open API, companies like, for instance, the Fraunhofer ERPT Institute, they have already developed some components. For instance, the BOM Cost Components, and with this component, we are able to really calculate the cost for this build job. So basically what happens here, you supply the information of the build platform and material data, density, support density, material price, the build rate, layer heights, even you can bring inside personal RM staff costs and so on. And with all this information, the component basically nests the part on the building platform. You can also create line supports. They can be visualized here. And in the end, you get here the total cost for this build job, the build time. And these are all relevant KPIs, of course, and very interesting. And also, we are collaborating with the IFU in Hamburg, and they have a lifecycle assessment software, Umberto, and also here we have done our first implementation as a third-party app. So based on the volume of the part and the material and the manufacturing process, which is here SLM, we can calculate the CO2 footprint of this part, which is here 23 kilograms, because these are very important aspects which are getting more and more important nowadays. So basically here we have the summary of our KPIs, and then we can back export our part to the as an STL or as a step file back to the PLM system, or in this case with RLE through the CATIA gateway, it goes back to the CATIA system. So
thank you. So
but
nice.
one interesting part is because before we jump to the next step is, I mean, this takes, of course, time to set up a DNA like this, but the cool thing is that now we can just change, we can replace it with a new part. So we have done that now for, let's say, for a steering knuckle for a medium-sized car.
I wanted to come to this point because, as we saw in the very beginning, so actually we do not totally focus on the part. Of course, this DNA now is for a steering knuckle. But David, what happens if we have steering knuckles with a slightly different design space, but they are comparable to that one? Can we just use this DNA?
Yeah, exactly. That's why I wanted to lead to exactly. So this is like, let's say, our first model. And now we can just load another model here inside. Let's say for a small car, maybe a Golf or something. And I mean, if we would do this now in the conventional product development process, we would have to start from scratch because it's a completely different geometry. We can also load maybe different materials and a little bit different, slightly different loads. So we would have to start from scratch, but in this case, since the principles of the part are still the same, so we can really automate the generation of parts, of part families, and that's a really interesting thing. So now what I will do is I will just load the new part, and as you can see here by these components, they're running through. This will take some time, of course, and now the components are processing the new information. And maybe in the meantime we can answer some questions, or maybe Tilman can say something more about the recycling, because I mean we have done that for the suspension control arm and the steering knuckle, but
I think
basically you can copy paste most of the workflow.
I think especially that recycling is a very interesting point, because in our case with that control arms, that we have just maybe we have set up that DNA for a front upper control arm or something, but that DNA then also works for the rear lower, for example, and that makes it really easy to update that kind of DNA and get new parts out of that. That's a very important point on the ELIS structure, I think.
Yeah, definitely. So of course, they have here some minor adjustments depending on the part you want to recreate. But in general, once you have such a workflow completely digitalized in ELIS, you can just copy paste it, and then you have already a really good starting point for the next product. So this is also one of the very, very unique selling points of ELIS. So I think Marin, I think.
Timon mentioned before that we are in early development and we can use those solid parts already. Maybe Timon can also show us later some further insights into the advantages.
Sure.
Okay, now we see the part. Nice.
Yes, we're already finished. So before we had here 6 parts because they were bigger, 3x2, and now the smaller one, of course, there are more parts fit on the build platform. So we have here 9 parts. So it's just then a question of computational power to recreate then the new build job.
Nice. Thank you, David. Thank you for this huge introduction into the process. I hope that our attendees now can better understand the whole process of how RLE set up the development process, but also how the internal process of release looks like developing parts. As I understood, Timon, it is very important and it makes a huge difference to use real solid parts in early stage development. Can you give us a quick insight into that?
Yeah, sure. Maybe I can share my screen again about that. Give me a second.
Yeah, of course. Just take it away.
Okay. So the next slide, maybe. Yeah, especially in the chassis case, in our opinion, that is a really important point to use designed or some kind of designed components in the early stage of the concept phase, because then we have the possibility to improve our, for example, kinematic concepts much earlier in the program. Means if we have that opportunity to do, we could achieve issues in the later on serial development phase, which maybe we also have the opportunity to reduce some prototyping phases, because we have all this information in the beginning of the project, and that means we can have a better understanding of what is necessary for the kinematic development. And I think that's the major challenge on that, is to centralize all that data which is necessary on that, because especially for a kinematic development, we need in a full vehicle kinematic development, we need that much information. For example, tire to street, or the friction between tire and street, or CGs and body weight, and all these stuff which is necessary for a proper kinematic development. And one of these things which is also very necessary is the flexibility of the components inside of that kinematic system, and this is something we can achieve with the ELIS application.
Nice. Okay. We have 1 minute left, and I think I would ask you to stay with us a couple of more minutes to answer some questions. If you can't, I'm really sorry, but I think we had to give this deep introduction. I think it's also very useful for all of you. And before you will leave, I will now quickly start a poll with 2 questions, which I would like you to answer. It would be really great. So the first question is exactly about this topic, and it's would you like to test multiple variants and iteration steps in early development? Is that something that's really important for you, or you're good to go the way you do right now? If you don't. Second one, do you already use automation interfaces between FEM and CAD? This would be really interesting for us to estimate generally, where customers go, where this companies go, in which directions, and yes. So I would be really pleased if you answers. I do just leave it here, and you can answer in between. So one last question, Tilman. First of all, thank you very much for all this deep insight into your processes, for sharing your expertise with us.
Thank you.
Yeah, thanks a lot. It's really awesome. Yeah.
It's really awesome, really helpful. But I think our attendees are also now, of course, wondering how they can implement such a process. So, yeah, could you give our listeners a hint about what are the, let's say, necessary steps to implement or test this in this process, or to implement and test GE in general?
Yeah, basically, I think we have to start with an easy kind of project or a small problem, and then scale that up later, because normally everything is possible in that kind of software, but if something is that new and creating that much more information, I think that could end up in maybe it's hard to understand in the beginning. So I think it is the easiest way to start with something small and scale that in the end.
Mm-hmm. Okay. Yeah, we suggest as well. So if you're interested generally in trying out ELEs, or would you like to have more information about how to implement that, of course, you're more than welcome to come back to us, but also, of course, to Tilman, to RLE.
Sure.
They already did that, and yes, so whatever problems you have regarding automation and product development, don't hesitate to come back to us directly. I will post our emails also in the chat right now, so you can write us or go to the company's page.
And yes, I think there's something which I want to say about that chassis process. So that's far not the end in the moment. There are so many ideas we have which could achieve that whole process, and a lot. For example, to get the direct contact to the kinematic tool, or get a direct contact to other optimization tools and so on. So this is something which will be improved in the future a lot. And I also think that this is something it's a logic step to go to generative engineering, because in the future I think it's all about staying competitive, and there's something which is the logic way to use generative engineering in the end, I think.
Yeah, great. We think so as well, and we hope so as well, of course. Okay, nice. So let's go back to your questions, and there are already some questions popping in. So first question would be, I just killed my screen. Okay. So first one we have here is there's a question from the chat. Can Elise handle casting or forged parts with manufacturing constraints such as draft angle and thicknesses? Maybe David, maybe can you say something about it?
Yes, definitely. It's also possible. You can define for the topology optimization just simply drawing direction constraints. And I think also in a couple of weeks we'll have a webinar also how we then, after the automatic conversion from ISO mesh or topology optimization with the quad measure to an IM part, there are some logics you can create to basically create automatically and also or convert this RM part into a feasible forging or casting part. And I think, yeah, in May we will have a webinar regarding this, and then you will see how that works in Elise, but it's definitely possible. Yeah.
Nice. I would love to.
I think
to
forging parts are a little easier than casting parts, because the geometry is not that complex normally. So
yeah.
Forging parts, I think this is something which could be possible already to use directly from Elise. Casting parts maybe are a little bit more difficult.
There's I mean, in general, at the current stage of Elise, I would say, as we have seen it also in the loop from RLE, is it's a very useful tool to generate in a short time many variations, but not maybe to the very last detail. So I think Tilman, you can definitely sign that. It's like, even if you get a part from Elise, still you need then to make all the detailed construction work of maybe putting the threads and the bolt cutouts and the final filleting and stuff. This little detailed work is not actually the major focus of our software. It's more like to generate in a short time many variations automatically. And then you
and getting information.
Yeah, maybe Tilman, you can give more information how it works. Yeah.
Okay. Getting informations earlier in the project, I think that's the major outcome from our process on the chassis development. Yeah.
That's more about the process. We have a look on the process itself and about gathering all relevant data before. That brings us right to the second question. What's the varying input that is used to generate multiple solutions inside Elise? Maybe this question was already answered with the presentation from David. But David, can you maybe say something quickly about what's necessary for the input we need to generate multiple solutions in the end?
Yeah, this can be basically different design, non-design spaces, or different material data. So we have seen in the Excel spreadsheet, there was Skalmalloy, the properties of Skalmalloy inside and of steel, but we could also extend this list to basically there are no limits. You can add titanium, aluminium, and so on. And these are always steered by parameters. So also loads, of course, which are implemented through an Excel spreadsheet. So everything which we have imported in the first section, this blue section, can be changed. And as soon as any of these components receive a new data, it will process the new information. And that's the trigger. We just have to change the data in the cables. And of course, this can be done by bringing new data from an external program, let's say CATIA or a kinematic program inside to Elise, or we can just change in Elise itself. Since we define everything parametrically also, we can just have sliders, and let's say we want to make a thickness optimization of a casting part with different ribs and stuff. We can just simply change the thicknesses of ribs or the heights of ribs by parameters, and then you can even connect these sliders to a parameter study or optimization, and overnight you can then run on all the you can generate automatically different variations of the part, and they are all evaluated regarding the boundary that the constraints basically.
Okay, thank you.
And maybe one thing I want to add on that, it's not only to get several versions back, you also have the possibility to run an internal optimization, which gives you back the, for example, best combination out of material, draw direction, and I don't know, several options. This is something I really think that is a huge advantage. Not just creating versions, also get an information which could be the best way to go.
Right. Okay. Definitely. So thanks to all our attendees who still staying with us. So we are 9 minutes over the time. So thank you very much for sharing this with us. There are still some open questions. if you don't have time, if you have to jump to the next meeting, that's how it is. But thank you very much for staying with us. And in the end, this webinar will be recorded, and we will also send it to you, and it will be also online. So we will continue now to answer some remaining questions. And if you're interested, you are still able to watch it afterwards. At this point, thanks also for filling out the poll. I will close it in around a minute. So if some of you haven't and would like to, just go for it. Otherwise, I will close it now. And thank you very much. There's another question. I think this is very interesting for everybody in kinematics. I would like to ask you, Tilman, is it possible to integrate and connect with atoms? Or first of all, I would like to say something that myself. So it is, as David mentioned and you saw before, has an open API. So theoretically, you can connect everything, but not everything is already connected. So if you would like to do so, you are able to join our developer program and program the components for yourself, and then also decide what to do with that. If you would like to sell them, if you would like to keep them confidential, or if you like to hand them out for free, like it's up on the corporation. And if you're interested in things like this, you can come back to us, and we can get in touch and we can discuss this problem. But not to Tilman, you needed to tackle with this problem. So how did you solve it?
That's to connecting atoms, or in our case, motion view, motion solve. That's basically an easy task, because the informations which are coming to Elise are just an Excel file, and it's basically the common way to get data from atoms or from motion view, motion solve. That's the common way to get an Excel file, and this is easy to input to Elise. So that's I don't see any issue to connect atoms. Maybe if you want to have a deep connection to manage stuff out of Elise directly into the atoms application, I don't know how to do that, but the easiest way is to use an Excel file.
Okay. Great. So it is possible, as you see, we can do that right now. So RLE did it, Tilman did it, and more advanced ways and how to connect and different kind of processes. Will be evaluated during alongside, let's say, our journey, integrating more tools and building up more and more processes. All right, I think now we really need to close down. If you still have more questions, and I see all the other questions, we will come back to that later on. So I will directly come to you personally, or I will forward that to Tilman. So questions will be answered. Thank you very much. First of all, Tilman, for joining us today.
Thank you for the invitation again. Thanks.
It was nice for having you here. Thanks also, David. David, who got us nice insight into the software. And thank you for all our listeners for hanging on with us so long, and for your interest. I would like to also introduce other webinars. So as David already mentioned, we have upcoming webinars regarding casting parts, and also regarding other topics about GE in general. I will send out invitations as usual, and I would be happy to see you here again the next time. Thanks again, and see you in the next time. Stay healthy, and have a nice end of the week.
Bye.
Goodbye, everybody.
Bye.